This is SpaceTime, Series 20, Episode 50, coming up on SpaceTime. The discovery that's rewritten galactic evolution, the new dark matter hypothesis, and how the Milky Way galaxy makes antimatter. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered the first example of a massive spiral galaxy similar to the Milky Way, but one which stopped making stars only a few billion years after the Big Bang. The study, reported in the journal Nature, challenges science's current understanding of how massive galaxies form and evolve early in the history of the universe. When astronomers first spotted the distant galaxy, they expected to see a chaotic ball of stars form through galaxies merging together. Instead, they saw a pancake-shaped spiral disk galaxy, similar in structure to the Milky Way. However, unlike other spiral galaxies which appear blue because they're constantly churning out lots of young new stars, this ancient spiral was more yellow in colour, full of old reddish stars, a clear sign that star formation had ceased, a characteristic more commonly associated in the local universe with giant elliptical galaxies. This is the first direct observational evidence that at least some of the earliest so-called dead galaxies evolved directly from spirals. The study's lead author, Søren Toft from the University of Copenhagen, says the new insight may force astronomers to rethink the whole cosmological context. Toft says the discovery means astronomers have been blind to the fact that some early dead galaxies could be spirals, simply because they've been unable to see them properly. Previous studies of distant dead galaxies always assumed that their structures would be similar to the local elliptical galaxies scientists always thought they'd eventually evolve into. But confirming this new understanding of galactic evolution will require far more powerful telescopes than are currently available. This discovery was made thanks to the phenomenon known as gravitational lensing. It involved an extremely massive foreground cluster of galaxies, known as MAX J2129-0741, which acted as a giant cosmic zoom lens in space, magnifying and stretching the image of a more distant background galaxy. By combining the gravitational lens with the resolving power of NASA's Hubble Space Telescope, the authors were able to see into the centre of the more distant dead galaxy. The remote galaxy, named MAX 2129-1, is located some 10 billion light-years away. And it's huge, with at least 3 times the mass of the Milky Way, but all compacted down to just half the Milky Way size. Rotational velocity measurements made with the European Southern Observatory's Very Large Telescope, the VLT, in Chile, showed that the stars in MAX 2129-1 rotate around the centre of this galaxy at over 500 kilometres per second, more than twice as fast as stars in the Milky Way. Using the cluster lensing and supernova survey with Hubble or CLASH archival data, Toft and colleagues were able to determine the stellar mass, star formation rates and ages of the stars in this ancient spiral. Astronomers believe young compact spiral disk-shaped galaxies such as the Milky Way will eventually evolve into old bloated giant elliptical galaxies through a process of mergers with other galaxies. These merging galaxies collide at all different angles, eventually randomizing the orbits of stars within the new galaxy. However, exactly why elliptical galaxies stopped producing stars way back in the early history of the universe has long puzzled astrophysicists. The most popular hypothesis speculates that collisions between galaxies would have provoked a sort of overproduction of stars within the galaxies, because all the available gas was compressed in their centres and transformed into billions of new stars through sudden starburst. With no fuel left for any more stars, these elliptical galaxies ended stellar production and died. However, with MAX 2129-1, things are obviously different. Although astronomers can say with certainty that this galaxy is no longer producing new stars and therefore can be safely considered stone dead, its existing stars are nevertheless still distributed in a rotating disk, exactly as can be seen in our own galaxy, the Milky Way. Why this spiral galaxy stopped forming stars is still unknown. It may be the result of an active galactic nucleus, where energy is gushing out from the galaxy's central supermassive black hole. This powerful energy stream could be blowing star-forming gas right out of the galaxy, literally starving it of the ability to form new stars. Alternatively, the energy from the black hole could be heating up the gas, preventing it from cooling to form molecular gas and dust clouds, which could then collapse to form new stars. Or it could be the result of cold gas streaming into the galaxy, being rapidly compressed and heated up, and again preventing it from cooling down into star-forming molecular clouds. Toft and colleagues are now hoping to use NASA's new James Webb Space Telescope to hunt for a larger sample size of similar galaxies. James Webb is slated to launch next year aboard a European Space Agency Ariane 5 rocket. It will be positioned in deep space orbit some 1.5 million kilometres from the Earth, from where it will be operating in a very cold and dark environment ideal for conducting observations. Its predecessor, the Hubble Space Telescope, was placed in a 500 kilometre high low Earth orbit. But James Webb is both larger and far more powerful than Hubble. It's designed to detect infrared light from the very first stars in the universe, making it possible for the first time to peer back to the very end of the cosmic dark ages and consequently see the birth of the very first galaxies. You're listening to Space Time. I'm Stuart Gary. Astronomers trying to understand dark matter may have a lot more work to do if a new hypothesis claiming there's more than one type of dark matter particle is correct. Dark matter is a mysterious invisible substance thought to make up some 80% of all the matter in the universe. It's called dark matter because scientists have absolutely no idea what it really is. Although they can't see it, astronomers know it's there because they can see its gravitational interaction with normal matter, the stuff stars, planets, trees, houses and people are made of. However, this normal or baryonic matter only makes up about 20% of all the matter in the universe. The rest is this mysterious dark matter. Understanding the true nature of dark matter has become one of the biggest questions in astronomy and physics over the past decade. The most widely accepted hypothesis for the makeup of dark matter is that it's probably composed of WIMPs, weakly interacting massive particles, which apparently only interact through gravity and the weak nuclear force. If they exist, these WIMPs will be composed of equally hypothetical supersymmetric particles, particles which can undergo annihilation interactions with themselves, possibly resulting in observable byproducts such as gamma rays and neutrinos. According to most hypotheses, dark matter particles would annihilate at the same rates in both small and large astronomical bodies, and across all times in the universe. However, the new hypothesis, being reported in the journal Physical Review Letters, claims dark matter annihilation rates are more rapid in the Milky Way galaxy than elsewhere in the universe. The authors have based their hypothesis on observations showing a lack of any signals from dark matter annihilation, except that is for some tantalizing gamma ray signals from the Milky Way itself, as seen by the Pamela and ASMO2 detectors and the Fermi Gamma Ray Space Telescope. However, these signals could be generated by other cosmic events, such as pulsars, supernovae, or matter-antimatter annihilations. The authors propose that this peculiar behaviour in annihilation rates stems from the symmetries of annihilating dark matter particles. Their hypothesis predicts that dark matter is made of more than one type of particle, and interacts through an as-yet undiscovered low-mass particle. If the dark matter origin for these signals can resist further scrutiny, and the signals aren't seen from anywhere else except the Milky Way, then their theory could explain why the Milky Way appears to be special. The absence of dark matter annihilation signals outside the Milky Way could therefore be a crucial hint towards a richer theory of dark matter, which would need to be tested by further observations. This is Space Time. I'm Stuart Gary. Faint supernova explosions caused by the merging of dead stars known as white dwarfs could explain how most of the antimatter in the Milky Way galaxy is created. The findings, reported in the journal Nature Astronomy, also mean the excessive gamma ray emissions detected towards the galactic centre can be explained without the need to postulate dark matter annihilation scenarios in order to explain the observations. As well as ruling out dark matter annihilation, the new study also dismisses Sagittarius A star, the supermassive black hole at the centre of the galaxy, as being a likely source for the antimatter. The Sagittarius A star supermassive black hole is located some 27,000 light-years away and contains some 4.3 million times the mass of the Sun. The study's lead author, Dr. Roland Crocker from the Australian National University, says the new research also provides some new insights into a part of the Milky Way where astronomers find some of the oldest stars in the galaxy. Antimatter is just the same as ordinary matter, but with the opposite electrical charge. So, the antimatter counterpart of the positively charged proton is the negatively charged antiproton. And the antimatter counterpart of the negatively charged electron is the positively charged positron. When matter and antimatter come into contact, they quickly annihilate each other, releasing a burst of energy in the form of gamma rays. Scientists have known since the early 1970s that the inner parts of the Milky Way galaxy were a strong source for gamma rays, indicating the possible existence of lots of antimatter. But there's been a lot of heated debate as to where the antimatter actually came from. The new work by Crocker and colleagues shows that the origins of this antimatter is a series of weak supernova explosions over millions of years, each created by the merger of two white dwarfs, which are the ultra-compact corpses of stars no larger than the Sun. For this to happen, the two white dwarfs have to be in a close binary system orbiting each other. The smaller of the two binary stars loses mass to the larger of the two stars, ending its life as a helium white dwarf, while the larger star ends up as a carbon-oxygen white dwarf. According to Crocker, the binary systems granted one final moment of extreme drama. As the white dwarfs orbit each other, the system loses energy to gravitational waves, causing them to spiral closer and closer together. Eventually, they get too close, and the carbon-oxygen white dwarf rips apart the companion star, whose helium quickly forms a dense shell covering the more massive star, triggering a thermonuclear supernova, generating antimatter positrons.
Positrons are the antimatter partners to electrons, and when positrons meet up with electrons in space, they annihilate with each other and produce a gamma ray signal, a characteristic gamma ray signal. So a similar process happens in positron emission tomography. A patient is injected with a radioactive material which produces positrons when it decays, and then those positrons produce gamma rays inside the body and use those gamma rays for imaging. So the same thing we think is happening in space.
This is because when we look towards the centre of the Milky Way, there's this gamma ray glow all over the place, isn't there?
That's right. So we see this characteristic gamma ray signature of positrons annihilating coming from the entire galaxy, but the signal is concentrated towards the inner parts of the galaxy, and it was first detected there almost 40 years ago with balloon-borne instruments, and instruments that have been on balloons and satellites since then have continued to detect the signal. And so the question has been, where do those antimatter positrons actually come from? And that's been a contentious issue for the decades since the signal was discovered.
As the research has continued, I take it astronomers have determined that it's not a really smooth sort of thing, but it's more speckled, isn't it? There seem to be point sources rather than some sort of a smooth emission which you'd expect from something like, say, dark matter.
There are individual sources, point sources of this emission, but in fact the distribution is rather smooth. So it's definitely been an idea. The interesting thing is that the strongest signal comes from the bulge of the galaxy. So the galaxies, you can basically think of it as a very, very thin disk, which if you look down on it, basically is circular. But in the center of that disk, there's a more or less spherical distribution of old stars. And then right in the center of that is the true center of the galaxy, and that's where there's a supermassive black hole. So this so-called bulge region of the galaxy is where the positron annihilation signal is strongest. And it's actually very hard to understand why that should be, because all of the stars essentially in this bulge region are very old, and they're not doing very much. So they're all old, low-mass stars. And basically in all other wavelengths, the galaxy is brightest in the extended disk, because that's where the galaxy continues to form stars.
That's where the young stars are. Yeah.
That's where the young stars are. So these are bright, very luminous stars, and they also live. They have short lives. The massive ones have short lives.
James Deans of the astronomical world, we call them.
Right, that's right. They live fast and die young. So there are no stars like that essentially in the bulge of the galaxy, and it's hard to understand why there should be this dramatic signal coming from that region of space. And so because the gamma ray signal of the positrons is concentrated in that region, and that's also fairly generically where you would expect the dark matter in the galaxy to be reaching its highest densities, the idea has been around, in fact, that the positrons might be the signature of dark matter. So dark matter particles themselves meeting up and self-annihilating, so-called, with it. So two dark matter particles annihilate with each other. So there's been that idea, and there's also been an idea that the supermassive black hole, so some process associated with a supermassive black hole might be producing the positron. So you're looking for something which explains why the signal is coming from towards the centre of the galaxy and is not seen as strongly from elsewhere in the galaxy. But obviously the dark matter or the supermassive black hole idea can't explain everything, because what's emerged over the last few years is that although it's true that the signal is strongest from this region of the galaxy, in fact we can also see the gamma rays from positron annihilation in the extended disk of the galaxy as well. So, dark matter or the supermassive black hole wouldn't explain why those positrons are being introduced into space in the disk of the galaxy. And so then you're left with this rather unsatisfactory situation where you're invoking one sort of mechanism potentially to explain these inner galaxy positrons and something else to explain this extended disk signal of the positron annihilation.
And we're also not seeing it in the halo, where there's also supposed to be a lot of dark matter. So again, that sort of leaves that out, doesn't it? It's sort of focusing in this one area of the galactic bulge.
That's right. So that's been the state of play, and what we realised in the course of our work was that you could actually come up with a single scenario or a single type of source which explained the entire distribution of positron annihilation in the galaxy. You could explain exactly why the signal is as strong as it is in the bulge, but also why it's there in the disk as well. And what we think is happening is that the positrons are being created by a particular sort of supernova, which only happens in stars that are old enough. So the basic idea is that these stars in the bulge of the galaxy, they're all rather old stars, and the supernova that we're claiming explains the galactic positrons, it occurs in binary white dwarf systems. And in particular, it occurs in binary white dwarfs where the white dwarfs themselves are rather low mass, and they've come from fairly low mass stars.
So these are sun-like stars that have reached the end of their lives. They've become white dwarfs after puffing off their outer layers, but because they're in binary systems, they've been stealing mass from their binary companion, and eventually they pass this Chandrasekhar limit of 1.4 solar masses, and they go through what we term a thermonuclear supernova.
That's right. So what's happening, actually, we think, is not a gradual accretion process. So we're left with, in these particular sorts of supernovae, these are thermonuclear supernovae, but they're somewhat unusual. They're actually dimmer than the usual type 1a supernova, thermonuclear supernova. And what is probably happening is that it's not a gradual accretion process, it's actually a merger between two white dwarfs. So these very old binary systems, they might seem to be not up to very much, but they very gradually lose energy because of gravitational radiation. And the white dwarfs spiral closer and closer to each other over time. And the particular systems that we're talking about or we're interested in are ones where you have a somewhat more massive white dwarf, which is a carbon-oxygen white dwarf, and the other white dwarf is a helium white dwarf. So the helium white dwarf has come from a star which is so low in mass that it couldn't undergo helium burning in its core. So it's basically burnt up its hydrogen fuel, and then its nuclear fusion processes couldn't go any further. So it's basically left as a white dwarf. Almost the entirety of its composition is helium. Now, so you're left with this binary system of helium, a lower mass helium white dwarf and a higher mass carbon-oxygen white dwarf, and it's gradually contracting over time as it emits gravitational radiation. And then eventually what happens is that the two white dwarfs get so close to each other that the stronger gravity of the heavier carbon-oxygen white dwarf completely disrupts the less massive helium white dwarf, and the helium and the two white dwarfs merge, with the helium from the less massive white dwarf covering the carbon-oxygen white dwarf in a very dense layer. So you end up with a merged white dwarf, which has a very dense helium layer on it as an outer shell, and that configuration is unstable. The very dense helium is primed basically to explode, which we think is what happens very quickly, and that produces the supernova. First, the helium shell explodes, and then that probably sets off the carbon-oxygen core of the merged remnant. But the whole thing is happening at a fairly low mass. It's actually not, it's below the Chandrasekhar mass, and it produces a subluminous thermonuclear explosion. But the peculiarity of the system is that you get fusion happening in all of this helium, and that then produces a particular radioisotope called 44 titanium. And it's from the 44 titanium that we think the positrons are coming.
The fascinating thing about this is when you have a star not able to fuse helium into anything heavier, I'm assuming that would need to be a red dwarf rather than a K or G-type star. It would have to be a spectral type M star?
Yes, so the star itself could be somewhat more massive, but because it's in a binary system, it's actually losing mass to accretion onto the primary and the white dwarf. So, in fact, it's possible for a single star not to be massive enough to fuse helium, but those stars actually have main sequence lifetimes, which are longer than the age of the universe.
Yeah, so that's what I thought.
Those stars, they're still burning. In the current universe, all of the helium white dwarfs that are there essentially have been produced in concert with some degree of mass stripping onto their binary companion.
Ah, right. Fascinating.
So there's mass transfer going on in this system. My colleague, Ashley Ritter, who's the second author on the paper, is responsible for all of these so-called binary population synthesis calculations, where she worked out the processes which have to occur in order that you get the right sort of configuration of a binary with a helium white dwarf and a carbon-oxygen white dwarf. Quite a narrow range for the initial masses and the separations between these stars. So the archetypal example of one of these supernovae is called supernova 1991 BG.
Okay.
These are SN 1991 BG-like supernovae that we think are happening. And in fact, they're not that unusual. It's just that they're hard to see because they're dim. They're probably something like 30% of all Type 1a supernovae.
Oh, wow. That's a lot.
So in external galaxies, in particular in elliptical galaxies where there's not a lot of dust to dim the supernova, these things are measured at that sort of rate, about 30%. But they're sort of an order of magnitude less luminous than an ordinary Type 1a. So what happens is that in our own galaxy, there's one of these things happening about every few hundred years, and each one produces a few hundredths of a solar mass of titanium-44. And the titanium-44 decays over a few decades, and it introduces, through the decay of the titanium-44, the positrons are injected into the space around the supernova remnant. But then the positrons themselves go on to live for maybe 1 million years in space. So they have to meet up in the rarefied conditions of space. They have to meet up with an electron with which they can annihilate, and it takes them probably 1 million years to do so. So when we look at the diffuse and rather smooth gamma ray emission annihilation radiation that we see in the galaxy, what we're seeing is the cumulative effect of many of these 91 BG supernovae happening over a long period of time, but each one, the positrons from each one are hanging around for about 1 million years.
What's the next step now? To look for these things, or is it just too dense there to find these things?
Yeah, well, certainly we would like to find supernova remnants that we could say, this is a good prospect for being a 91 BG on the basis of the unusual elemental composition of the X-ray emitting plasma in the remnant, or through other means of determining the composition. So I have a graduate student, Fiona Panther, who's also a co-author on the paper, and she is looking into what we can find out about these 91 BGs out in the rest of the universe. So they're observed in external galaxies,
yep.
And our research suggests that, unlike basically all other supernovae, these supernovae, because they're delayed so long after the formation of the stars from which they're created, they're delayed so long that the rate that they're happening should be actually increasing now in cosmological time. So that means if we look back at higher,
further back in space,
then the rate of these things should actually be smaller. So we're hoping to make that measurement and confirm that hypothesis, basically. The existing data are consistent, but the uncertainties attached to it are pretty big. The other really suggestive thing that I can say is that there's another mysterious signal which is in high-energy astrophysics, which is connected to the bulge of the galaxy and which has also been claimed as a potential signature of dark matter annihilation. And there's something called the galactic center excess. This is another higher energy gamma ray signal, which is, really does look like what you might expect from the annihilation of WIMP dark matter in the bulge of the galaxy. But we think we can explain that same signal through similar processes as to what we've identified here. So not exactly the same supernovae, but the same population of binary white dwarfs. We suspect at the higher mass end of that population, of those higher mass white dwarfs, the oxygen, neon, magnesium white dwarfs, ones which are either accreting from a companion or which merge with a companion. It's the same process as you introduced earlier. So these things can be very close to the Chandrasekhar mass for an oxygen neon magnesium white dwarf, if they approach the Chandrasekhar mass, they don't actually explode, at least according to some theories. What they do is they just collapse immediately down into a neutron star.
Okay.
And
wow.
This is a process called accretion-induced collapse. And the neutron star, which is produced directly from that process, is also very rapidly spinning. And so basically what you get from these events is a millisecond pulsar. Yeah. And the galactic center excess, although I said it really does look like a very good prospect to be a dark matter signal, by the same token, it also looks spectrally like the sort of signature you get from millisecond pulsars. Their spectrum looks rather similar to the excess.
Is that the research being done using Fermi, the millisecond?
Yeah, that's right. Yeah, it's really looking now like that this so-called galactic center excess is probably not a dark matter signal, and other considerations, it looks like it might come from these millisecond pulsars or maybe from ordinary pulsars, which emit gamma rays. But the work that we've done on the positrons is potentially providing a mechanism to supply the millisecond pulsars which would be required to explain that different signal.
It's teaching us more about the evolution of stars.
Yes, hopefully. So yeah, it's an interesting thing to see that even really, really old stars or stellar populations have still got a bit of life in them. I mean, you might think that just two white dwarfs orbiting each other in a binary system is the ultimately boring system where nothing ever happens. But because they slowly contract, the binary will slowly contract because of gravitational radiation or other processes, even these sort of apparently boring systems can have a final, spectacular burst of energy associated with the merger right at the end of their lives.
A last hurrah.
A last hurrah, exactly.
That's Dr. Roland Crocker from the Australian National University. And you're listening to SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at Spacetime with Stuart Gary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. NASA is today slated to launch its newest mission to study the interstellar medium, the space between the stars. Deep in space between stars isn't empty. Instead, there are charged plasma particles and vast clouds of neutral atoms and molecules, which over millions of years can evolve into new generations of stars and planets. These drifting interstellar reservoirs are the focus of the new mission to check out the earliest stages of star formation. NASA's mission is called the Colorado High Resolution Echelle Stellar Spectrograph, or CHESS, and it's slated to blast off from the White Sands Missile Range in New Mexico aboard a Black Brant 9 suborbital sounding rocket. CHESS works by measuring light filtering through the interstellar medium in order to study the atoms and molecules within the medium, providing crucial information about the life cycle of stars. CHESS is designed to measure light filtering through the interstellar medium in order to study the atoms and molecules within that medium. CHESS principal investigator Kevin France from the University of Colorado in Boulder says the interstellar medium, which pervades the entire galaxy, is filled with raw materials expelled by massive stars when they explode as supernovae. It's this material from the insides of dead stars which eventually fuels the next generation of stars and planets. Put simply, CHESS is a spectrograph, providing information on how much of any given wavelength of light is present. It'll train its eye on Beta Scorpii, a hot, brightly shining star in the Scorpius constellation, well positioned for the instrument to probe the material between the star and our solar system. As light from Beta Scorpii streams towards the Earth, atoms and molecules in the interstellar medium, including carbon, oxygen and hydrogen, block this light to varying degrees along the way. Scientists already know which wavelengths are going to be blocked by what. So, by looking at how much of this light reaches the space around Earth, they can assess all sorts of details about the space this light travelled through in order to get here. CHESS data will provide observations such as which atoms and molecules are present in space, what their temperatures are, and how fast they're moving. Scientists will also use CHESS data to evaluate how the interstellar cloud is structured, and that can help them pinpoint where it stands in the process of star formation. It's still not known exactly how long it takes for this material to be incorporated into new stars. But scientists do know that dense molecular clouds can eventually collapse in on themselves, forming stellar nurseries where future generations of stars and their planetary systems will be born. The short ballistic flight of the Black Brant 9 sounding rocket will only last about 16 minutes, and just 6.5 of those minutes will be spent actually making the necessary observations between altitudes of 150 and 320 kilometres above the ground. These observations can only be made in space, above the atmosphere, which the far ultraviolet light that CHESS observes can't penetrate. After the mission, the payload parachutes back to the ground, where it can be recovered for future flights. In fact, this mission's the third flight for the CHESS payload in the past 3 years, and it's the mission's most detailed survey yet. Scientists use each flight to trial and improve the technology. In fact, the current mission uses an upgraded diffraction grating, which will reflect light and separate it into different wavelengths. A more efficient grating means the instrument will be many times more sensitive. In fact, compared to the first flight of CHESS, this third incarnation is about 8 times more sensitive. By flying rapidly developing instruments on relatively inexpensive sounding rockets, scientists are not only able to acquire high-quality science data, but they're also able to test and mature their instruments for use in future more advanced missions over the next few decades. In fact, the CHESS instrument's already serving as a spectrograph prototype for future NASA missions. I'm Stuart Gary. You're listening to SpaceTime. China has launched its first space-based X-ray telescope. The telescope's designed to survey the Milky Way and study celestial X-ray sources such as neutron stars, black holes and supernovae. The Hard X-ray Modulation Telescope was flown into orbit aboard a Long March 4B rocket from the Jiuquan Satellite Launch Center in the Gobi Desert of Inner Mongolia. The spacecraft's fitted with 3 X-ray telescopes, one for high, one for medium and one for low energy sources. This enables it to make multiple observations which previously would require different satellites. The observatory will help scientists creating new high-precision hard X-ray maps of the sky, and also help them study black holes and the strong magnetic fields around neutron stars. The spacecraft's scientific instruments were powered up 5 days after reaching orbit and are now undergoing 140 days of on-orbit calibrations and test observations. The telescope's first round of scientific observations is planned to start in November, with second-round observation proposals expected to be collected by mid-2018. You're listening to SpaceTime. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.